Hello again, welcome to Sciencing Around. This time we are studying the most important part, or I must say some important part of modern physics, that is X-rays. As you can see here, I've written it, nothing but X-rays. So let's get started, shall we? I hope that I need not have to explain what's an X-ray because I hope that you all know what is an X-ray. So here you can see that I've just made what is the production of X-ray, as that comes as the first part. Now you can see it's a type of machine, or I must say a type of chamber, where water is used as coolant. Here it's a type of filament, I must say. From these filaments electrons are ejected. Now what are electrons are ejected to? You can see I've written here a target metal. It's a target metal. Electrons are ejected to the target metal. This target metal can be anything, any metal with high boiling point somehow. So electrons are ejected to the target metal with a very high potential difference, very high, and it's an anode. And as the potential difference of the electrons are very high, the heat becomes very more, and thus water is used as coolant. Of course, the electricity is passed through this. Uh, Intensity must be very high, of course, because the electrons are at a very high velocity, and as they are in very high velocity, some different types of waves or rays or electromagnetic waves are let's just left out from this target metal, and this is nothing but X-rays. You must have seen an X-ray machine. All this stuff happens inside an X-ray machine, and waves come out. You just put your hand in front of this thing, this wave, and you get a print of your hand inside, the bone print of your hands. I think that was enough for X-rays. Now let's get down to the properties of X-rays. So the properties of X-rays, the first point says that highly penetrating rays can pass through several materials which are opaque. Since the X-rays are very highly penetrating, they can just pass through several materials, several solid materials, such as your skin, but not your bones. They ionize the gas through which they pass. They can ionize any gas from He, no, not He, CO2, CO2 plus, or any fucking gas. They cause fluorescence in several materials. Now, what is fluorescence? I hope you would all know. And they are not deflected by electric and magnetic fields. That's the very important part. Because they are highly penetrating rays, so they're not deflected. They show all properties of waves except refraction. It shows reflection but not refraction. I don't know why. That's the property, of course. Now, X-ray absorption. What's this all about? Now let's see. If I naught be the intensity of incident beam and I be the intensity of a beam after penetrating in thickness x, then I equals to I naught into e power minus of nu times x. Oh my god, what's that? If I naught is the intensity of incident beam, that means the beam which is incident, that means the original intensity is I naught, and I is the final intensity when it's penetrated in any material of thickness x, then I equals to I naught into e power minus of nu x, where nu is the coefficient of absorption, depends on metal and metal. Nu depends on wavelength of X-rays, density, and atomic number of material. Yes, nu depends on these all. Elements of high atomic masses and density absorbs X-ray to higher degree. That's elements which have higher atomic masses, like anything. We can say francium, radium, plumbum. Any fucking element with higher atomic mass and density can absorb X-ray. Yeah, because they have X-rays have more penetrative properties, so elements with higher atomic mass can absorb this. So next page, let's do. And now we have Bragg's law with us. Now what does this say? That when X-ray beams are incident on a crystal, path difference is 2d sine theta. Theta be any angle of incidence or anything, and m lambda, where m is an integer, or sorry, m is order of diffraction, m lambda equals to 2d sine of theta. Theta is the gradient angle. Yes, it's the gradient angle, the angle of changing. D is intraatomic distance. It should be given in any question. M is the order of diffraction. And interatomic distance is same order as lambda. That means lambda is in angstroms, then D is also in angstroms. That's it. Now X-ray spectra and origin in X-rays. This again includes the series, the K series, L series and all that stuff. Now X-rays are of two types, characteristic X-rays and continuous X-rays. Now what are characteristic X-rays? Now let's study. They consist of several radiations with sharp wavelength. I'm sorry for the wrong view. They consist of several radiations with sharp wavelength and frequency. Similar to hydrogen spectrum, this type helps us to find element of target metal. So they consist of radiations with sharp wavelength. Yes, they have sharp wavelength, frequency. I'll show you the graph afterwards. Similar to hydrogen spectrum, this type helps us to find element of target metal. That's good. When X-rays penetrate into the atom, it kicks out an electron by colliding into it. I'll tell you by diagram in some other page because this page is full of theory. So just now learn when X-rays penetrate into the atom, it kicks out an electron by just colliding into it. Just that in its shell, electron is missing. Thus, an electron from outer shell comes to that inner shell to fill the vacancy, thus radiating energy, whose frequency is RZE square, where E is 1.6 into 10 power minus 19. That is RZE square into 1 upon n1 square minus 1 upon n2 square, where z is equal to z minus sigma. It's totally different topic. It's a shielding constant. I'll tell you afterwards. Thus, it should not be remembered. Fuck this thing. Thus, another vacancy is created and the outer shell. Yes, because the outer shell electron goes to the inner shell, so another vacancy is created, which is filled by another outer shell. That's interesting. The transition of electron from various outer shell to innermost shell from K series further divided into K alpha, K beta, K gamma, all depending from outer shell from which transition is made. So let me show you a diagram. Now what is this? See, if it's a nucleus, this is the nucleus. It's the first orbit. It's the second fucking orbit. And it's the third orbit. Alright, these are electrons. 1, 2, 2 electrons here. 2, 3, 4. Here we have 5, here we have 6, here we have 7, here we have 8. And let 2 electrons be here. Nothing, atomic mass 20, potassium, calcium, sorry. So we put an X-ray right here. It's an X-ray, penetrates here, comes again, comes again, comes again, falls at this electron. This electron gets displaced. Then electron from this shell takes the place of this shell, and electron from this shell takes the place of this shell. This depends by, we can now just divide these groups in K series, L series, M series. Since K electron is displaced, this is from K series. Let's get down to the theory part again. I hope you know how this thing happens. The transition of electron from various outer shells to innermost shells forms K series, further dividing to K alpha, K beta, K gamma, depending upon outer shell from which transition is made. That's it. Now what is Moseley's law now in this page? Under root of frequency, that is of X-rays, under root of X-ray frequency equals to A times Z minus B, where A and B are almost fucking constants again. A and B are constants and B is screening constant. It should be sigma, alright, but it's okay. I can understand. Now we have X-ray series, just explaining K series, L series, M series and all that stuff. Now see, N is equal to 1. Since the first orbit transition is made, first line is K alpha, then K beta, then K gamma, and then K delta, and increasing from that thing. Now this is L series, you can say N equals to 2, K, L, M, all that stuff. So it's L alpha, L beta, L gamma. It's N equals to 3, and K, L, M, it's M alpha and M beta, and it's N, so N alpha. X-ray series, I think it was quite easy. Just K series, L series, M series, N series. That is simply if it comes from the second orbit to the first orbit, it's K alpha. If third orbit to first orbit, it's K beta. from third orbit to fourth, from third to fourth it's k beta, from fourth to first it's k gamma, and going on till infinity. Now here from infinity to first it's k alpha, in 3 to 2 it's beta. I'm sorry, what I'm saying. You know what? Rip me off. It's L alpha, it's L beta, and it's L gamma, because from 3 to 2 it's L alpha, from 4 to 2 it's L beta, and so on. L gamma can be anything. Right from here 4 to 3 it's M alpha, from infinity to 3 it's L beta. Beta depends on anything. Infinity to 4 it's N alpha and all that stuff. Like that it thing continues. Now let's see about continuous X-rays. The tubes also emits the continuous X-rays of varying intensity, wavelengths, and independent of material. They end abruptly at the certain low wavelength, where the minimum wavelength is at C by nu, where nu is the voltage. It's at C by V, where V is the voltage applied. That's interesting. Now let's look at the graphs. Now the lambda versus the intensity graph. That is the wavelength versus intensity graph. That is k gamma, k beta, k alpha. K alpha having the biggest wavelength, k beta having the least of that, k gamma having the least of k series, but more than L series, of course. It's L alpha, L beta just less than L alpha, and M series, and so on. Now what are continuous X-rays? Continuous X-rays, now I will mark something for you. This thing and this thing are continuous X-rays, and the thing you can see which came up, that are nothing but characteristic X-rays. Continuous X-rays are nothing, they just emerge along with the characteristic X-rays, and characteristic X-rays having the most importance, that is with high wavelengths and all that stuff, high intensity, of course, as you can see, as the wavelength increases intensity, that is this k alpha, k beta, k gamma, and all that stuff, because these are characteristic X-rays, the thing which came up, and continuous X-rays are these things. As they are continuous, they are continuous. How can I explain more? So next page, should we? Oops. So guys, we completed with X-rays. Now I hope you saw the nuclear physics right now. We'll do it in some next lecture. The time is too long, the video is too long. I want your support. So if you like this video, don't forget to like the video, don't forget to subscribe my channel, and if you don't like the video, alright, then please tell me what did I do wrong, how should I teach to make this lecture more interactive. Thank you very much, see you soon, happy sciencing.